In the last segment, we talked about percent volume by volume as a usable unit when your solute is in milliliters and your solution is in milliliters. However, usually and typically you have a solid in grams dissolved in water, which will make a solution that is in milliliters. So percent mass by volume is the typical unit you would use moving forward. Okay, so for example, a question might be, what is the percent mass by volume of glucose in a solution prepared by dissolving 10.0 grams of glucose in enough water to make 250 milliliters of solution? Well, your glucose is your solute, and that is in grams. Your solution is in milliliters, so that is in volume. So 10.0 divided by 250 times 100%. Push some buttons on your calculator, and you get 4.00% mass by volume. Now again, like the other percents, when you have a unit in the numerator and a unit in the denominator, that's your signal that these can be used as conversion factors. And here is an application. If a patient order indicates that a person should receive 500 milliliters of this glucose solution, what mass has been delivered? So all along, I've been giving you a process, a starting place, an ending place, and then convert. So when you get questions like this, you've been doing these all along. They just sound a little different, but the process is the same. 500 milliliters of solution over 1 is our starting place. Grams of glucose is what we're looking for. And our thought process in going from milliliters of solution to grams of glucose means we need a percent mass by volume. And so what this means is we're going to use this to say 4.00 grams of glucose per 100 milliliters of solution. That's the definition of percent, is 100. Milliliters of solution cancel. 3 sig figs here, 3 sig figs here, 3 sig figs in our answer. Push some buttons, and we end up with 20.0 grams of glucose. Okay? The next question is, what is the percent mass by volume of a solution containing 7.5 grams of casein in 120 milliliters of low-fat milk? This is in grams, this is in milliliters. The casein, we have less of that, so that is your solute. The milk is your solution. So remember, milk is not the same as water. Milk is the solution. Okay? So our percent mass by volume is 7.5 grams per 120 milliliters times 100%. We push some buttons on our calculator. We get 6.3% mass by volume. Now, FYI, casein is the protein that you find in milk. So there might be some kind of generic sort of application like we have here. So the question that I have in your notes, if the generic amount of protein required for an average adult is approximately 55 grams of protein per day, what percent of the requirement is met by this small amount of milk? Okay, 120 milliliters is about a half a cup. So for some people, depending on how much coffee you drink in the morning and if you keep pouring milk in, this might be the amount of milk that you put in your coffee in the morning. Okay? Now this is not a conversion. This is simply a question that says, okay, if I have 7.5 grams here divided by 55 grams that is required times 100%, this represents about 14% of what we would need in a day. So the application is not using this as a conversion factor, it's going back to the original information. Nonetheless, you could ask yourself something like, how many milliliters of milk would you need to meet this requirement? In other words, if you didn't consume any animal products in a day, you didn't eat any hamburgers, you didn't eat any bacon, you didn't eat any eggs, all you had was milk. And that was all you had available to get your 55 grams. How many milliliters would you need? Okay, so our starting place is 55 grams of protein over 1. Milliliters of milk is what we're looking for. So we have to ask ourselves, what piece of information do we know that's going to relate grams of protein per milliliters of milk? And it's our percent mass by volume. So we have 100 milliliters of milk divided by 6.3 grams of protein, which is the casein. That's the definition of 6.3%. When we do that, we get 870 milliliters of milk, which, granted, is a lot. That's about 3 quarts. That's a lot. Nonetheless, the idea is to show the conversion, but also the tangential aside of showing that most people, most of the time, don't need to eat an animal product for breakfast, lunch, and dinner to get the amount of protein that most people, most of the time, need in an average diet. Okay, next page. How many grams of sodium hydroxide are needed to prepare 3.00 liters of 15% mass by volume sodium hydroxide solution? Okay, so what we have here is our magic word that we're going to love, and that is the word of. And of, when we talk about math, of means we're going to multiply. Okay, multiply. Okay, so 3.00 liters times 15.0 grams per 100 milliliters. That's our definition of 15.0%. Now we see we have a unit problem, so we're going to have to fix that. 1,000 milliliters over 1 liter. And all we've done is figured out where we're going to start, and we haven't even looked at what the question is asking. The question is asking how many grams. Well, we have that unit. So by simply recognizing the word of and indicating that we're going to start multiplying, and we're going to be manipulating our units so that they cancel, we don't even have to really do any work. We have the unit that we want. We don't have to convert to moles. We don't have to convert anything. And so this is why, from the very beginning, I've told you, embrace your process. Pick your starting place, pick your ending place, cancel your units, and go from there. And the units will do the work for you, as it has in this particular problem. You do the math, you push some buttons on your calculator, you might get 450 with a whole bunch of trailing zeros, depending on what your calculator is displaying for you. 3 sig figs here, 3 sig figs here. So 450 grams with a decimal is how we want to express our final answer. Okay? So you're going to want to practice these in terms of figuring out the percent itself and figuring out how you're going to apply these. Okay? Because at the end of the day, percents are great and well and good and all, but in chemistry, the unit that we use most of the time is molarity. Molarity, by definition, gets the symbol capital M, which is moles of solute per liter of solution, because we want moles to lead us back to the actual chemical equation that will allow us to do solution stoichiometry.